Good morning, everybody. This is David coming to you with some more mind-blowing research. Today is especially mind-blowing, so I hope you have your hats on, especially Daniel Pratt. You know, he likes to wear his hat. The first thing I want to talk about, I want to talk today about global winds. And I borrowed this PowerPoint from this website here, but it's publicly available and you can find it on many different websites. Before I get into that, let me give you this research from Iowa State University. Here's the website down here. I know this is a long paragraph, but I want to read this to you. The orientation of the Earth with respect to the Sun produces a semi-regular circulation pattern of the winds around the globe. The large-scale wind patterns are so produced are called the general circulation. Large-scale air movement helps to produce the climate of different areas. The patterns are generally similar in the northern and southern hemispheres with some slight differences, which we'll show you. The driving force for the winds is the sun. Heating differences produce heat imbalances, which produces wind. Since the sun is nearly overhead every day of the year in the area near the equator, it is very warm. Warm air tends to rise, but that air is going to go somewhere. It doesn't just rise out into space. It moves toward the North Pole or the South Pole, attempting to balance the heat difference between the equator and the poles. If the Earth did not rotate, this air would flow directly to the North Pole or South Pole. Sinking at the poles, the cold air would flow back to the equator and complete a circulation cell, which I'll show you. This type of circulation is called Hadley circulation, or the circulation that the Earth would have if it were not rotating, named after the meteorologist who theorized it. Since the Earth does rotate, it has a more complicated circulation caused by the rotation. Here is that Hadley cell. It says on a non-rotating planet, heated air from the equator would rise and move toward the poles, cool, and sink. The cold air from the poles would then flow toward the equator, completing the circulation pattern. So here is this Hadley cell from the side view. So you have warm air at the equator that rises. It moves toward the poles, both directions. When it does, it starts to cool and it descends at the pole. Then it starts to move south because of the high pressure and the low pressure down here. So it starts to move south. And then when it gets down here, it becomes warm again. And we repeat that pattern. So that's called the Hadley cell, which is not what we see in real life. So what causes wind? We talked about a little before. Wind is caused by the movement of air, which is caused by the differences in air pressure. Differences in air pressure are caused by the uneven heating and cooling of the Earth. Warm air is less dense and creates an area of low pressure. Cold air is more dense and creates an area of high pressure. So we get this kind of pattern, and this is measured by weather balloons. It's observed every day on the weather if you watch your weather channel or whatever. So you have the trade winds here near the equator, equatorial doldrums, which we'll talk about. You have the westerlies, and then at the poles you have the easterlies. This is what it would look like on a flat Earth if the winds were as we measure them. This is what they would look like. So the polar would go around this way, the westerlies would go around this way, the easterlies would go this way. Oh, I'm sorry, these are trade winds, would go this way. There's the equator with the doldrums. Again, the trade winds go this way. You can see both sets of trade winds go, what is that? East to west. Then we have the westerlies, which go from west to east. And then at the South Pole, we also have easterlies, which go from east to west. I couldn't draw those in because of PowerPoint. So you see, we have kind of a mess here. There is no explanation for why the winds would switch directions at certain points. There's no explanation for why at the equator we have the doldrums, or why the winds swap directions in the southern hemisphere. So if anybody knows how to do that, I hope you'll let me know. Trade winds. So in the middle here we have the trade winds. They all move from east to west. In the northern hemisphere, they move from northeast to southwest. In the southern hemisphere, they move from southeast to northwest. Our westerlies, right here, so they move from west to east. And again, in the northern hemisphere, it's from southwest to northeast. In the southern hemisphere, it's from northwest to southeast. The polar easterlies, those go from east to west in both hemispheres. In the north, they go from north to south, northeast to southwest. In the southern hemisphere, they go from southeast to northwest. And the polar easterlies carry cold Arctic air. The westerlies, we talk about again. The westerlies are between 30 and 60 degrees latitude. They flow toward the poles from west to east. Like we talked about before, they flow in a different direction in the north hemisphere than they do in the southern hemisphere. This affects the weather in the United States. This is where I live. And almost every day on the weather, they talk about the west winds flowing from southwest to northeast. Occasionally there are local low pressure areas or whatever and that cause differences, but the prevailing winds are from southwest to northeast. The trade winds that blow from 30 degrees to almost the equator. These winds are named for the fact that these winds move sailors across the Atlantic Ocean from Europe to the Americas. And so you remember Columbus, Magellan, all these guys, they went from east to west using the trade winds. And again, in the north and the south, they're different. So the north flows southwest, and the south flows northwest. And then the trade winds meet at an area called the doldrums. This area is located around the equator at 0 degrees latitude and it's usually like plus or minus 5 degrees. This is an area of low pressure where there's very little wind. I think I'm going to move there. Located at 30 degrees north and 30 degrees south is an area of little wind also at these latitudes. The name given by sailors who got stuck here because of lack of wind. Travel time was slow. They were called the horse latitudes because horses were thrown overboard to save water. I thought that's kind of creepy. The curving of winds due to the Earth's rotation is called the Coriolis effect. I know most of you flat earthers don't believe in the Coriolis effect, but because of this Coriolis effect, winds curve to the east and west. Winds traveling north curve to the right or east. Winds traveling south curve to the left or west. This always happens, and again, it's because of the Coriolis effect, which is because the Earth is rotating. And as an aside here, if you want to see an awesome explanation of the Coriolis effect, check out Baldy Catz, and here is his website. I'll put it in the description. I really want you to go there and watch that. While you're there, be sure to like and subscribe. The jet stream, we always hear about this jet stream. These are narrow belts of high-speed winds that blow in the upper troposphere and lower stratosphere. Unlike global winds, jet streams do not follow regular paths. Knowing the path of the jet stream can help airline pilots travel faster as they ride the jet stream. Here once again, you flat earthers, you're always talking about how shouldn't planes be able to go faster going east than they do going west? Well, lo and behold, it works that way. Meteorologists can track a storm if they know the location of the jet stream. Here are the local winds. Local winds move short distances and can blow from any direction. Geographic features such as a shoreline or a mountain can produce temperature differences because that's the way it works. You can have a sea breeze, a land breeze, a mountain breeze, or a valley breeze. And that's not really the scope of this video, but we can talk about those later. And that's all I have for today. Again, be sure and go check out Baldy Catz. That's one super intelligent guy.